So very good. What we were talking about last time. So very good. What we were talking about last time was to complete the analysis of multi-staging. And in particular, we were analyzing the case, and we concluded last class analyzing the case of two-stage vehicle having the same inert mass fraction but a different specific impulse. And you have seen that in this case, of course, that the best condition consider the different specific impulse as a weight that will balance the sharing of delta V towards the stage showing higher specific impulse. And you have seen we have analyzed the distribution of delta V among the two stages, and we have seen that there is a preference towards the stage with higher specific impulse. And we can also say, I don't know if I said this at the end of last class, that this sharing depends on the ratio delta V over specific impulse. So, and on epsilon. So also on the contribution of epsilon. So when we have higher value of epsilon or higher value of delta V, the difference in specific impulse will weight less, because delta V over a specific impulse will be less different if delta V is larger. Anyway, this was just to start from what we have seen last time. Today I would like to give you a few words about parallel staging. It's better to write black. So with parallel staging, what we mean? So what you have seen so far is what is called tandem staging, or what the meaning is that we are considering one stage at a time, one after the other, like in a row. So that was called tandem staging. So we have in this case something like this: first stage, second stage, third stage. Whereas what will be the parallel staging? Parallel staging means that we are using, at least for a given time, two stages at the same time. So we have typically a sustainer stage, called this way, which will operate for a given time, and for part of its operation time there will be, for instance, another stage working in parallel. So this can be is interesting for different reasons that I will mention shortly, and typically for the first stage. So parallel staging is related to the lift-off maneuver. The reason is that it can be interesting to get a quick acceleration. We have seen the reason that we have to reduce the time needed to fly vertically leaving the atmosphere. And considering a parallel staging, we can, let's say, provide a higher acceleration for a short time. Of course, there is a cost. You see already on this sketch I did, you see already that there is, even by this, that there is a difference in terms of aerodynamic losses. And you see that parallel staging will provide higher aerodynamic losses, for sure. But it can be still of interest. It's also true that in this case, again, with tandem staging, you can optimize each engine for the range of altitude of its operation. Whereas in this case, you have this sustained stage that must be started at takeoff and will work for a longer time on a long trajectory. So how you will analyze? Typically, you consider more than one parallel stage here. So because of this goal that is given by the research through this parallel staging of having a boost at the beginning, a higher thrust in the initial phase, typically we call it the parallel stage, we call it boosters. So boosters are, for instance, these two side rockets that would provide an increase of thrust at liftoff. This is the typical case, and you see that hidden in this concept there is also the possibility to having something which is let's say in a standard way, so that we have a generic booster, and we can use, in principle, we can define different rockets, just changing the number of boosters we are using. And these provide us with more flexibility in terms of the payload we have to lift to orbit. So for the analysis, what can be done? Because we have seen here the first subrocket, the second subrocket. So this was, the first one was the whole rocket, and the second one, the whole rocket minus stage one, and so on. What shall we do in the case of parallel staging? We will proceed in the same way. The only difference is that the first stage will be made of the core stage plus boosters, and we have to consider for this first stage only the amount of propellant of the core stage that is used together with the boosters while boosters are operating. Then we will pass to the second stage, where there will be only the core stage, but with less amount of propellant, because we have consumed part of the propellant during the parallel operation. So if we consider that, so we can identify here inside, let's say, a propellant mass divided in two parts. For instance, this part here is consumed during the first stage, so with parallel, during parallel operation, and then we will use this other part of propellant. So the first thing to do to analyze the first subrocket, so the first subrocket will be the whole launcher. The second subrocket will be the first subrocket minus what will be discarded, which are the boosters. Notice that we have some inert mass that will be, for instance, will be tanks of propellant that will not be discarded despite we are consuming propellant for the core stage. So what we have to do here for the first subrocket, the first thing to do is to consider its specific impulse. Because in this case we are operating different engines, typically, because to have also good density of propellant, they can be, for instance, not necessarily solid rockets as the boosters, and for instance a liquid one for the core stage, so they may have quite different specific impulses. So what will be the specific impulse of the booster? We know that we have to make the weighted average of specific impulses by the mass flow rate, or define our specific impulse as, let's say, the ratio between thrust and propellant mass flow rate. Well, we have here the thrust generated by the core plus the number of boosters multiplied by the thrust generated by each booster divided by the propellant flow rate of the core plus n times number of boosters by the propellant mass flow rate of the booster. So we already seen this. So when we are going to evaluate our delta V or payload ratio of the first stage, of course we need also the inert mass fraction. And inert mass fraction here, of course, is defined as usual. Let's say epsilon 1 will be the inert mass fraction of each booster and then over the same, yes, I use just B, so it's quicker now. And then we have the propellant using boosters plus the propellant used we have here propellant, let's say core, let's say 1. So what's strange here is that we don't tell the inert mass fraction corresponding to that propellant, which is that of the core, and the reason is that this will be payload for this first stage. It's because it's something that will remain also when the boosters are discarded. So here we have, but the propellant must be included because we have to consider the inert mass fraction with respect to the propellant that we have, and this will make that our relationships will continue to be valid also for this case. Then we have, on the other hand, what happens for this first stage. At this point, we have will have some more inert mass with respect to the what will be needed by that propellant, because we have some container, let's say, that has been used to contain the propellant used in the first stage. So we can say that the core propellant mass will be core 1 plus core 2, and epsilon 2 will be the inert mass of core divided by itself plus the mass of propellant used in this second stage. So once we have our epsilon, we have defined it according to the definition we have used before, because we have, of course, we have specific impulse, we have our inert mass fraction defined the same way, and our propellant mass fraction epsilon is defined as inert divided by inert plus propellant, and so we can proceed as done for the tandem staging. See an example or something in more detail. So we consider an example, the above example of a booster plus sustainer. So we may have something which is known information about the booster and sustainer by themselves, independently of their combination. So for instance, we know that we have a given thrust. So we have FB, we have Fs, so is boosters plus sustainer are our stages. So we have the number of boosters and a specific impulse of booster and of the sustainer, that in general will be different. We have also here, we can define some inert mass fraction of the booster and of the sustainer that will be different from what we have seen before. These are characterizing each of these parts. So this will be MSP divided by MSB plus MPB, and this will be MSS plus MSS MPS. Based on the thrust level and specific impulses, we can also consider the propellant mass flow rates that will be dot MPB equal FB over UEQB and dot MPS Fs over UEQ S. It can be convenient now introduce some relation among these quantities, among the features of the booster and of the sustainer. And in particular, we will introduce ratio alpha, which is the relative amount of propellant mass flow rate. We define this as MB.MB. Consider that this is just an example. They are not general definitions. You can define the quantities as you consider more convenient. So you see here, this is the mass the propellant flow rate exhausted by the boosters compared with the overall propellant flow rate of the stage. Then we can introduce a ratio between the thrust of a booster and thrust of sustainer, and of the specific impulse of the booster and specific impulse of the sustainer, and also the ratio between the propellant mass used by the sustainer during the boosted phase and the overall propellant mass of the sustainer. So at this point, of course, we have to consider the delta V of each phase of the boosted and sustained phase. So we have delta V1 and the delta V2, and to them will correspond, of course, some Z or MR that will be, of course, directly related to this delta V through the rocket equation. So we have that MR is equal to E to the minus delta V over specific impulse, or for Z will be 1 minus the exponential of delta V over the specific impulse. And so at this point, with these quantities, as we have seen, we can try to rebuild our epsilon 1 and epsilon 2 and see what happens. Let's try to give some general hints. And of course, for the specific impulse, I will repeat, in this case, with this ratio of quantities. In this case will be S sine plus NS FB over M dot NB dot NPB, and this can be obtained by considering that here, of course, F is dot MP by specific impulse. This will be, of course, corresponding to the average specific impulses averaged by the mass flow rates, that means through this alpha. So this will be the specific impulse of the first stage, the first equivalent stage, and we can also express this in terms of the ratio of the thrust of the two components, booster and sustainer. In this way, where you see that this beta you see above is the ratio between the thrust of the booster and thrust of the sustainer. So this will be, to evaluate our Z1 and MR1, we need this quantity. and this quantity, delta V1 and the specific impulse. For the second stage, we know that it's quite simple. UVQ of the second stage, of course, there will be only the sustainer, because we have that during if the first stage includes, for instance, 2 boosters here, the second stage will be after discarding these 2 boosters, so will remain just the core part, of course with always the same engine, and so always the same specific impulse, if you are not considering changes of specific impulse that will necessarily occur with altitude. So I record just here the expression of lambda. And so to get lambda, of course, we need our epsilon 1 and epsilon 2. We have seen that epsilon 1 is defined as we have seen before, so NB MSB over NB MSB plus, so this is the inert mass of the booster, and then we have the propellant mass NB MPB plus MPS1, and we recall that the definition that we have just provided of epsilon b, so that 1 over epsilon b, if you go back and you see, is ms over ms plus mp, so you make the inverse, you have ms plus mp divided by ms, so 1 over epsilon b will be 1 plus ms mpb over msb. And this allows us to divide now. If in epsilon 1 I divide everything by NB MSB, it will be here 1, then 1 plus MPB over MSB plus MPS1 over NB MSB. So at this point we can notice that in fact there is a relation. Once we know the propellant flow rates and of the booster and of sustainer, we also know the ratio, the relation between the propellant mass of the booster and the propellant mass of the sustainer, which is used together with the boosters, because we have a given time that we are considering. So we can say that MPB is dot MPB by T. We consider constant this mass flow rate. At the same time, we have that MPS1 is the amount of propellant which is used during time TB. And so we can say that MPS1 is equal to MPB by dot MPS dot MPB. So we can resort to our ratios, and here dot NP is F S U eq S, F B U eq B, MPB, and this Fs over Fb is sorry, Fb over Fs is beta, and UQB over UQS is Y, so PS1 is Y over beta MPB. And so you see that we can make appear again here MPB over MSB, that is the same that we have on this step. Here, completing the expression of epsilon 1, we see that here we have 1 plus blah blah is just 1 over epsilon b. And then we have y b and b beta b MPB over MSB is 1 over epsilon minus 1, so it's 1 minus epsilon over epsilon. And at the end we see that once we know the ratio between thrust and specific impulse of the sustainer and the booster, we can express the value of epsilon 1. That will no longer depend on time and other things. It's just fixed on the basis of the above ratios. Okay. The other thing that we have to do is to evaluate epsilon 2, and also here we can exploit our ratios that we have introduced. So we have that epsilon 2 is equal to MSS plus MP S2 Of course, we can make appear the MPS1, which is related to booster operation. Also here you can exploit 1 over epsilon s is equal to 1 plus MP over MS. And so we have 1, divide everything by MSS, 1 plus MPS MSS minus MPS1 MSS. So this is 1 over epsilon changed by this quantity. So as if you compare the two expressions, you see that for the case of epsilon 1, if you go to this expression, you have an additional term here in the denominator with respect to the case, but you have only, if you consider the case without, the basic case is epsilon b and corresponds to this denominator without this term. In the present case, we have an additional term here that you don't see. Yes, you see. We have an additional term that tells us that this quantity is less. So the inert mass fraction for the first stage is lower because part of the masses are considered as a payload. Whereas, on the other hand, if you go to epsilon 2, you see that at denominator we have a subtracting term that tell that here we have a lot of inert mass fraction because we have also the part that contained the propellant before. And so this MPS1 or MSS can be rearranged as 1 over epsilon s minus, this is mu1 MSS1 MPS over MSS, which is 1 over epsilon minus 1. And so we have this second expression for this. This is for the epsilon 2. Okay, now let's make a further step and consider, let's try to see, as we have done for the case of two stages with different specific impulse, we have considered that the available delta V partitioned in delta V1 and delta V2, and we say that let's consider that delta V1 is x delta V and delta V2 is 1 minus x delta V. So we have a target delta V that must be realized, and we can analyze the behavior of the payload mass fraction as a function of the distribution of this delta V between the two stages. So this was done for at the end of last class, considering different specific impulses, and we made some consideration, and we can do this also here. So in this case, of course, if we go back to the expression of lambda, of course, the overall lambda will be the product of lambda will be a function of x, and this product of lambda 1 and lambda 2, all is function of x, because in the expression of lambda there is delta V. If we go here, we see that we have that here we have a dependence on x. This is not the case for epsilon 1, because we have seen that epsilon 1 is just does not depend on the delta V we are considering. It's just a matter of the ratio between the performance of the booster and sustainer. So we see that here we have this dependence on x, whereas we have to consider now that our epsilon 2 is a function of this partitioning, and this is because mu1 is in turn a function of the partitioning. Let's see this. Because we have to consider mu1 as MPS1. Of course, this is rather reasonable, because we will consume part depending on how much delta V we provide to the first or the second stage. There will be an amount of propellant of the core stage that will be used in the first phase and in the second phase. So it's rather obvious that this quantity will depend on this x. And we can see this by considering now that MP1 will be equal to of course MPS1 plus MV MPB. So it's the amount of propellant used in the sustainer and the overall propellant of the booster. And of course this amount of propellant is also the one corresponding to the mass fraction multiplied by the propellant mass fraction multiplied by the initial mass. On the other hand, we will have that also a relation with the propellant mass fraction is also valid for the second stage. But in this case, we have to consider the initial mass of the second stage. And what is this? It's the payload of the first stage. Right? So we can exploit then the relation between masses here of the propellant for the booster and for sustainer that we have already written, because we know the flow rates and the fact that they are operating for the same time to evaluate this MPS1 and MPB. And so we recall that MPS1 is equal to Y over beta by MPB. So we can substitute here in mu1, and of course the M0 will disappear, and we have that mu1 is equal to Z1. So here we can express MPS1 exploiting this relation. MPB will be MPS1 divided by YB over beta. So we have NB beta over Y and 1 plus NB beta over Y. So this is the expression of MPS1 as a function of M0. And this is also a denominator divided by 1 plus MB beta B divided YB plus MPS2. Now this is MP1, sorry. MPS2, which is equal to MP2 and so it will be equal to zeta 2 lambda 1. And so of course here the dependence on x is here, here, here and here. And so we clearly see that this quantity will be depending on the partitioning between the two stages. So to conclude this part, I would like also to put some numbers inside, and considering the let's say numerical example, that means something like the space transportation systems as the order of magnitude of the quantities. We have delta V that can be 9 9,000 meters per second, and we can consider MB equal to 2, and we can also consider epsilon B equal to 0.11, epsilon S equal to 0.15, U EQ B 2600 meters per second, U EQ S 4000 meters per second. Approximated values of different parts, and also that FB is equal to 12.5 meganewtons and Fs is equal to 5.2 meganewtons, so that we can easily evaluate the relevant quantities. In particular, we can, according to the quantity we have defined before, we have beta, which is equal to 2.4, and we have also y, which is equal to 0.65, alpha is 0.881, and as a consequence the result will be epsilon 1, which is 0.0973, and you see that it's less than the inert mass fraction of the booster. With these quantities, at this point we can plot. We have this number, these ratios, and are those that we need. We have also delta V. We can plot the behavior of lambda as a function of x. Also here we have an optimal position that allows to get the maximum lambda, and we have that x can be between 25 and 55% to have a positive payload, and we have a peak at about 40. So we have that the peak is at about x equal to 0.4 and corresponds to epsilon 2, which is 0.22, to be compared with 0.15, which was the actual value of the sustainer. So you see that here this means that 40% of the delta V is provided by the combination of the sustainer stage with the booster, and then the remaining 60% by the second part. You see that it's something similar to what we have seen with the two stages, and we also see that also in this case we are optimizing by considering more delta V for the stage characterized by a higher specific impulse. Note, of course, that here in this case we are also changing between the two stages the value of epsilon, which was not the case in the last class example. And the final thing before we make a break of 5 minutes, I just would like to conclude this part of parallel staging saying that from this example, this numerical example, we can also compute the time spent in the boosted phase, and we can evaluate this time as MP1 over dot MP1, and this will be theta M0 divided by this MP1 will be also the thrust over the average specific impulse. So if we assume that this F0 is alpha m0 g0, this is the initial acceleration that for liftoff must be greater than 1, we realize here the expression theta 1 over alpha and u eq1 over g0. So this is a specific impulse in seconds. So this time will be proportional to the specific impulse in seconds of the first stage multiplied by the ratio between the propellant mass fraction and the initial acceleration level. Considering alpha 1.5, we can plot t as a function of x. Of course, the interesting part is the one between 25 and 55%, and we can also identify here the 40%, which is the optimal condition, and we see that this time is obviously increasing with x, means that the increasing x means that we have more propellant used in the first stage. So you see here that we have this increasing value, and an interesting solution with just these approximate numbers, which is under 35 seconds here. It would be here 105 and here 150, which is not far from what was the real case, where this phase was about a couple of minutes long. So we take a break now for 5 minutes, not more because we started later, and we resume at 1:15.
Scusi professore.
Sì, prego.
E non è che potrebbe gentilmente ripetere perché ε1 risulta essere sempre minore di εb e ε2 maggiore di εs?
Sì, la ragione è che c'è una massa che è quella che contiene il propellente del sustainer, che non è il propellente che è usato nella prima fase. Questa massa è attribuita come carico utile al primo stadio, perché sarà parte di ciò che verrà rilasciato una volta scaricati i booster, mentre sarà una massa inerte senza propellente nel secondo stadio. Quindi in pratica nel primo stadio ci troviamo una massa di propellente che non ha associata una massa inerte corrispondente, quella del sustainer usata nel primo stadio, e al contrario nel secondo stadio abbiamo una massa inerte che non è associata al propellente. Per cui abbiamo una massa in meno al primo stadio, e questo fa sì, aggiungiamo solo propellente, quindi diventa che la frazione di massa inerte diventa più piccola, e abbiamo una massa in più inerte nel secondo stadio, che fa sì che quella diventi, il suo contributo sia maggiore.
Va bene, grazie. Scusi professore, non so se sta spiegando, però è mutato, noi non la sentiamo. Non so se stava spiegando.
Ahimè, ha perfettamente ragione, per cui adesso devo riavvolgere il nastro. Scusatemi. So let's go back and restart. I was talking about possible advantages. I was concluding the discussion of parallel staging, and in particular of pros and cons of this parallel staging. In particular, among the advantages, the higher acceleration and the consequent reduction of gravity losses, the possibility to have more flexibility considering a different number of boosters, the reduction of the vehicle height, and also in a two-stage launcher, for instance, that all the engines can be ignited at sea level. As possible disadvantages, we have to consider the higher aerodynamic losses, and this is especially true for small rockets, as we have underlined, and also the limits in the optimization of core stage, because it must be optimized for the whole trajectory rather than only for the upper part of the trajectory. So, of course, one of the points that have been underlined is that of the size of the vehicle, and if you see different vehicles, you can find that the slender bodies of small vehicles and, let's say, more blunt shape of large vehicles. And this is exactly related to the fact that smaller vehicles are more suffering of aerodynamic losses or drag losses. So once we have completed this part describing the basics for staging of rockets, now we start a different part, and we pass to discuss thermal rockets. So what we do now is to pass, because what we have seen so far is to introduce, to classify, to analyze the basic performance parameters, to also underline what are the needs for a rocket in terms of, I mentioned delta V and the importance of this quantity, the amount of propellant, specific impulse, but in launchers and in space maneuvers. Of course, launchers have been discussed a little bit more in detail because of the need of staging, and I mentioned when we introduced the need of staging, this was related to the fact that we have a limited specific impulse that we can reach. It's a direct consequence. We need 9 km per second to reach orbit. We have 4.5 km per second specific impulse maximum with chemical rockets. So in general, the next step is to see why you have this upper limit, where the energy comes from, and how we can use this energy in our rockets. And most of rockets are, or at least all rockets for launch vehicle, are are thermal rockets. So we recall that thermal rockets we have classified rockets with in different way based on the way we use to accelerate the propellant, and we have seen that this can be based on thermal or thermodynamic process, on electrical or electrodynamic process, or nuclear. And the thermal case is the one where we wish to convert the internal energy in kinetic energy of the jet. So the available thermal energy. We call this also a gas dynamic conversion of energy, and often we use also this term to refer to this thermal or thermodynamic acceleration. I will use thermal acceleration for which seems to be shorter. And of course, to make this, if you like, now if we try to imagine how to use the internal energy to have high speed, we can imagine that this is not so easy if I consider a solid as the propellant. If propellant is a solid, like the stones we've seen at the beginning, if this is hot as internal energy in some way, it doesn't seem to be an advantage when I have to eject it. It's also true for the liquid that the internal energy I can imagine if I use a liquid as the medium for propulsion. I imagine something that is like pressure. If I have higher pressure, I can imagine that I have a jet of liquid, visible. But probably if you think of something hot or cold, it doesn't change much for a liquid. Different is the case of gases. So at the end, to exploit the internal energy, the temperature, let's say, that is a measure of the internal energy of the medium, you have to consider gases. And so to analyze how in gases we can exploit the internal energy of gases to get high speed jets, we have to recall something of thermodynamics. So we will make in these two classes, I think a couple of classes, a brief review of some thermodynamic concept. So we start considering a pure substance. And it's useful now to recall what are the state variable, what is the equilibrium state, and what are the basic laws of thermodynamics. So first of all, we consider in thermodynamics a system which is made by a fluid which can be in principle a liquid or a gas, and we can here we consider first pure substance. That means it's a single species in our system. So this system is said to be in equilibrium if it has been left for a long time enough without interaction with surroundings, and enough means that it has reached a final state that is no longer changing. And this is what we call the equilibrium state. So in this equilibrium state, our system will be characterized by specific quantities that we refer to as state variables, so that we will describe this state, typically pressure, volume, temperature, density. In general, among the variables describing this state, we can identify intensive and extensive variables. Extensive are those that depend on the size of the system or let's say on the mass of the system, whereas intensive are those which are not. And for every extensive variables, we can define a corresponding intensive variables, which is obtained by the ratio of this variable to this extensive variable to the mass of the system. So we have a specific quantity which becomes also an intensive variable. So moreover, we will recall that a thermodynamic system is identified by two state variables. For a pure substance, it is completely defined by two state variables. This will be a thermodynamic fluid. And this means that as we talked about many state variables so far, I said that they are intensive, extensive, pressure, volume, temperature, density, and so on. It means that there will be some relation that allow us to determine all the variables once we know two of them. These relations are called equations of state. And in particular, we can identify the thermal equation of state and caloric equation of state. We'll talk about this in a minute. Before doing this, let's consider that we have to define temperature. This comes from the zero law of thermodynamics. Let's say that if we have two bodies in contact with each other that can exchange heat, they will be in equilibrium when they are characterized by a quantity that we can call temperature that is equal for the two bodies. It's the same for the two bodies. So we can say that state variable temperature exists such that two systems in contact with each other can exchange heat from one another are in equilibrium only if they have the same temperature. And similarly, we have if this zero law introduces temperature, the first law of thermodynamics introduces the internal energy, and the second law of thermodynamics introduces the entropy. We have, as I mentioned, about the equation of state. So once we have introduced temperature and, or we will reintroduce temperature and internal energy and other quantities, we have that the basic equation of state will relate pressure, temperature, and volume, and this will be the thermal equation of state. Whereas the caloric equation of state is the one relating the energy, the internal energy, to the other state variables. And the equation of state, so relating the different quantities, represents the behavior of our substance that comes from the interaction among the particle that makes this substance. So we can get equation of state from the experience or from the statistical mechanics, so that analyze the behavior of particles through the collisions and the volume forces that may exert with each other. So this will yield our equation of state. So let's recall briefly the first law of thermodynamics. And here what we can recall is that this is a special case of the law of conservation of energy, and usually we refer to an enclosure like this, closed by a piston, and we have a gas here inside at a given pressure. We can act with a force here, and we can also provide heat from outside to this gas. So what we consider here is that if we push against this pressure and move the piston, we will make a work, and this work will be that we are releasing energy toward the gas. At the same time, if I'm providing this heat, I'm also changing the energy of the gas. And so there should be a state variable that allow us to evaluate how much energy is inside this gas. And this is the internal energy. So we say that if I'm providing it or I'm making work through this force, there will be a change of the internal energy. So we see the difference between the internal energy and this Q and W. Q and W are, let's say, transit energy is something that we are providing to the gas. The internal energy represents the content of energy of that gas. So if you are providing in some way energy to this gas, its internal content will change accordingly. So Q and W will depend on the process that we are considering. We can provide this heat slowly or suddenly. We can make this work slowly or suddenly. The internal energy represents instead the final result, the change of energy content of the gas. So in this case, we can evaluate this work as the force by displacement, and we have a force against the pressure. This pressure will be exerted along that surface, so the force will be pressure by area, and area by the displacement will be exactly the change of volume of the gas. So in this case, we can say that our change, let's say the elementary change of internal energy, comes from the heat coming from outside minus P dV, where this is the volume, that of course will be, there will be a positive work made toward the gas providing energy if we are decreasing the volume of the gas. So this is the reason of this minus here. And this internal energy, you see that here I'm considering the whole volume of the gas and the work made on this volume. So these are all extensive quantity. Of course, here this is extensive, and extensive. Pressure is intensive one. And we can refer these quantities to the unit mass of the gas, and this will become, dividing by this mass, the specific internal energy will be equal to this delta Q minus P dV, where this is the specific volume, which is the inverse of the density. It's the volume per unit mass. So the next step is also to make some further comment on this transit energy and to emphasize the difference between reversible and irreversible processes. We have irreversible processes are those which are spontaneous processes, and all irreversible processes depends on the fact that there are so-called currents, that mean fluxes. So there are differences of quantities that allow some transit of energy occur. So these currents are, for instance, if there is a difference of temperature, there will be net flux. If there is a difference of momentum, there will be a diffusion in terms of momentum, so through viscosity. If there is difference of species, if we leave the case of substance, there can be also difference of species, and there will be a mass diffusion. So these are the currents that allow to realize that move towards an equilibrium through irreversible processes. On the other hand, a process can be considered as reversible the process can be said as reversible if there are no currents. That means that if there are changes are so small that there are no current can be identified. So it means that if we have to move from reversibly from one state to another, we have to progress by a sequence of equilibrium states. So we don't see a change, the presence of currents. So of course the reversible process is an ideal one and can be, however, we can try to reach this process, to have something similar through special experiments. We can imagine, for instance, the case of making work on a fluid, considering a rotating wheel with blades fastly rotating, and this is probably making work, and this is typically an irreversible process. But we can imagine that we use a piston which is moving at infinitesimal velocity. We make a work also in this case, but for each infinitesimal displacement of the piston, the gas has time enough to reach a new equilibrium state. If you move it quickly, you will have different conditions within the gas because there is no time to reach a new state of equilibrium at each displacement of the piston. So we mentioned the relationship among the different state variables. We have to consider in general. We can consider that the equation of state, the thermal equation of state, that relates different quantities, and we will refer always to the perfect gas equation of state. We have to consider that if the fact that we consider the perfect gas equation of state assumes that we are in a well-defined region of the range of possible variation of pressure and temperature. We recall that we have, for instance, here a tripod point, a saturation curve, and we have here solid, here liquid, and here we have vapor. These are different regions, and we identify here what is called the critical point. Là si vede. Non si vede. Can you see the PT diagram from home? Ma secondo me da casa lo vedono.
Sì, lo vedo.
Ok, grazie. Questo è indipendente, quindi se voi lo vedete lì va bene comunque. So you see that there are different regions and we have solid, liquid and vapor. You know this, of course, but it's important to say here that we have, for instance, here what we call gas, and we call here a supercritical fluid, and here we have a compressed fluid. So to the region of gases, let's say, is of course, so where you can use the perfect gas law is, let's say, here for sure, and it can extend also to higher pressure when we are sufficiently far from the critical point. So, of course, what is difference? What is the assumption of perfect gas is that the interaction among particles is just through collisions. There are no volume forces that are exchanged among the particles, so molecules, and whereas this is not the case when we have liquid, or we have dense fluids, or we have supercritical fluids. In these cases, there are volume forces that become important, and so the equation of state will change. In this region, we can use the ideal gas equation of state, and this will be the region that we will cover in this course. So the equation of state of perfect gases is well known. We can write it in different ways, as you know, in this way for sure, but we can write it also as related to kilomole. This is pressure volume equal number of moles, the universal gas constant, and temperature. So we have that this quantity is in terms of kilomole, joule, Kelvin. Pressure volume is as a dimension of joule, and we can also use the way to express the equation of state starting from single particles, and from kinetic gas theory we can obtain P equal mkt. This is the same equation of state, but in this case we have pressure, the number of particles per unit volume, the Boltzmann constant, and temperature. Boltzmann constant, which is 1.38 joule Kelvin. So this is n particles per unit volume. So these two equations are related to each other through the constants of Avogadro. Let's say how many particles are in a mole. So you can express the equation of state considering a reference quantity, that represents the amount of fluid that we are considering. So this can be moles, can be mass, can be particles. And as a consequence, we have a similar but different equation of state, and we can move from one another. So among so if we consider here that this n, if we multiply here this n by, so this will be a huge number. Here I missed something. Sorry. This way it wouldn't work. It was 10 to minus 23 because we have a huge number here in the particle per unit volume. So if we consider now set of particles per unit volume, we divide by 6.02 10 26, which is the number of particles per these particles per kilomole. Multiplied by this quantity, we have the number of moles, and so you have that if you consider the number of moles per unit volume, this is at A, the Avogadro number, and this was the relation we have written before, and here if we now P equal nkt, we consider multiply and divide by LA, you see that here this is exactly n over V, the same quantity, and so we have here that LA by K must be equal to R, and so you can check that multiplying the Avogadro number by the Boltzmann constant, we obtain the universal gas constant. So when we move in other parts of this diagram, if we are not far from the perfect gas condition, we can use a correction factor, which is the compressibility factor called Z, that will allow us to write P equal to Z O RT. I'm passing now to this expression where with the density. That means that I'm passing from considering moles, particles. I can also use mass. If I use mass, I should consider in this case the P equal RT. I should consider the fact that the number of particles will be related to the mass of the particles, the overall mass divided by the mass of the particles. And so if I consider that density will be given by the mass of the particle by the number of particles per unit volume, so this is also can be expressed as the molar mass, so the mass of a mole by the number of moles per unit volume, and I make substitution, and so that I can obtain that N over V is the number of moles per unit volume is equal to density over the molar mass. And so P is equal to mv RT rho m RT, and our gas constant is defined as the ratio of the universal gas constant to molar mass of the substance we are considering. And we can see this also from the equation of state written in terms of particles, P equal nkt, and you have here P equal rho n over mu. Sorry, n is no longer here, it's k over mu t, right? N is rho over mu, yes. So you see that R is also the Boltzmann constant divided by the mass of the particle. So I will stop here for today, and we'll continue tomorrow by this. I will recall something about specific heats and entropy. That is something needed to go then to the discussions of the conversion of internal energy to kinetic energy.
Scusi, professore,
Prego.
ma su Mu abbiamo definito la massa molare?